Welcome back. I'm Dr. Lukes, and this is Material and Energy Balances. So we're now starting Chapter 3, which is on processes and process variables. Again, this is another chapter that should be somewhat familiar, but we probably are going to stretch these concepts a little further than you're accustomed to. Really read this chapter for the hidden gems that are in the book. So first, let's talk about mass and volume. Usually what we do to find data, we're going to usually talk about density. Density uses rho, the Greek letter rho. It's mass per unit volume, and it's a very common variable. We also, however, frequently talk about specific volume. Specific volume is really just the reciprocal of density, but it's volume per unit mass. Then one other kind of variation on this is specific gravity. Specific gravity is frequently listed in data tables. It's just simply a dimensionless form of the density. Specific gravity is the density divided by the density of some reference substance. Now, this is going to vary from time to time. You need to really be sure what the data table says, but typically for solids and liquids, use liquid water at 4 degrees C, which has the density of 1 gram per cubic centimeter, or 1,000 kilograms per cubic meter, or 62.43 pounds mass per cubic foot. The advantage of specific gravity is I can use any of those systems of units and it will still work. Now for gases, there's a lot more variability in what they'll use. Typically it's air, but it might not be. So always look at the table and see what they say is the reference state for gas-specific gravity. Now density is going to vary with temperature and pressure. In thermodynamics, you'll learn a lot more about that variation. But for now, just be aware that when they specify these, it's usually only at certain temperatures and pressures, and those are usually listed in the data table. We also frequently want to talk about flow rate. Okay? So how quickly a stream flows is going to be a flow rate. This may be a mass flow rate or a volumetric flow rate. Now ideally these little things are written as M with a dot on the top of it or V with a dot on the top of it. It's very difficult to get Microsoft products to want to do a dot on the top of a variable. So I will tend to put the little dot next to it, and I realize that that's very hard to read also. Now the mass flow rate and the volumetric flow rate are going to be related to each other through the density. So density is mass per unit volume, but it also would be mass flow rate divided by volumetric flow rate. Now we're going to be measuring flow rates in all chemical industries. Usually we use various forms of flow meters. Some of the simple ones are a rotometer or an orifice meter. Now there's all sorts of different kinds of flow meters, and one of the really nice things, you can link to this through Wiley Plus, but the Chemie Equipment Encyclopedia. And if you do that, you're going to see that you can look at different kinds of flow meters, and it will show you how they work, and in fact you can watch videos of how they work. So I'll let you peruse that on your own later. So, chemical composition, another very common thing that we want to use when we describe chemicals. One of the things that's actually probably what distinguishes us the most from other disciplines is that we need to account for mixtures of chemicals. And this can be done in either moles or mass units, and it can be done in either SI or American engineering units. And this is one of the first places where people start going, at this course, because this is new. Okay? So let's talk first about molecular mass. So M, the molecular mass or molecular weight, it's usually presented without units in the appendix of the book or in data tables. You can also get this from periodic tables, plus knowing the chemical formula for your molecule. We are typically taught that the molecular mass of a substance has units of grams per mole where a mole is defined by Avogadro's number. 1 mole has 6.02 times 10 to the 23 molecules of whatever that thing is. Okay? Now that's true, okay, but the number of molecules that make up a mole is only true with the CGS system of units. That's the one that uses grams, okay? Now, grams are really not handy if you're talking about things on an industrial scale. If you want to know how many grams in a 5-pound bag of flour or something like that, then that's not an outrageous number. But when you start talking about how many grams are in a storage tank that you see as you drive down the highway, that's going to become an unwieldy number. So we rarely use grams, which means we're rarely going to use moles. There are other moles available. Okay? The mole that you are used to is more precisely known as a gram mole, or we'll just write G mole, or sometimes we'll just leave it as MOL. Okay? If we're using that kind of mole, then Avogadro's number is valid, okay? And we're going to measure the molecular mass in grams per mole, or grams per gram mole. If I want to do SI units, this doesn't seem like much of a stretch, because usually I use mass in kilograms. And the sort of mole that matches that is, instead of a gram mole, it's going to be a kilogram mole. Or we often call it a kilomole. And the nice thing is that since a gram to a kilogram multiplied by 1,000, a mole to a kilomole multiplied by 1,000. Okay? But we also want to be able to work in those English or American engineering units. Now we typically measure our mass in pounds mass. And the appropriate mole measurement is a pound mole. So the units for the molecular mass are going to be pounds mass per pound mole. Now, how many molecules is that? I don't know. You could do the math and figure it out. It's a unit conversion problem. But I also don't care. I am never going to sit and count the molecules. So to me, a mole is a convenient way of knowing that the molecules have been counted, okay, by some mythical someone out there. So it's accounting for molecules, whereas the mass is accounting for the mass of the substance. And so a pound mole correlates to a pound mass. So for instance, if you looked up, say, nitrogen, it says that M is 28.02. You can use this as 28.02 grams per mole, 28.02 kilograms per kilomole, or 28.02 pounds mass per pound mole, whichever of those is most convenient. We're also going to be talking about compositions of things that are combinations of many chemicals, and so we want to talk about that composition, and frequently we use a mass fraction or a mole fraction. Now we're going to be doing more of this in the next little lesson, but in this lesson I want to just get the concept out there. So a mass fraction is the mass of species I, okay, the mass of water in this mixture that has a lot of other things as well as water. So I'm going to take the mass of the water, or whatever, divided by the total mass. If I want to do a mole fraction, I simply take the moles of that species and divide by the total moles. Okay? If I want it to be in percent, you just multiply by that fraction by 100. So the mass percent is going to be 100 times the mass fraction. The mole percent is 100 times the mole fraction. Okay? Now we are, for the first half of the course, going to try to make an effort to use X for mass fraction and Y for mole fraction. That's going to evaporate in the latter half of the class. Okay? Just to kind of make sure that you're getting used to this. There isn't a true firm definition of which one is which. Okay? We usually use those guys late in the alphabet, but we could call it anything. You just want to make sure that you're specifying it's mass of A per mass total. Okay? Sometimes we will have weight fractions used. Now, mass is going to be the same, right, from location to location. Weight changes, But assuming that the species is in a mixture and the gravitational field is the same throughout, then a weight fraction will be exactly the same as the mass fraction. Now, one more little fact I want you to know. Okay, first of all, well, I guess this is two more little facts. Okay, first thing is that a lot of times people will just say it's a percent of something, okay? And so they'll say, oh, well, this mixture is 23% air, or it's, 58% methane, okay? And they don't tell you what type of percent. There is a tradition, okay? Typically, when you are doing gases, it is going to be a mole fraction that is going to be what's measured and read. Typically, if you are doing liquids, it's easier to measure mass fractions, and so that's typically what's used. So if people do not tell you what type of fraction or percent they're using, these are the assumptions that you should take. The second thing that you should remember is that the fractions are always a piece of the whole, right? So if I had a mixture of A and B and it's 25% A, well, then the rest of it has to be B, so those two need to add up to 1, so therefore 75% B. And this would be true for mole fractions and for mole fractions. So we're going to come back in the next lesson and we're going to talk a little bit more about how mass and mole fractions are related to one another using our new definitions of moles.